So, my name is Rob Beverly, and I'm here to tell you about some work that myself and some colleagues at MIT, Steve Bauer in particular, did called the Spoofer Project. So, as I'm sure many of the people in this audience are well aware of spoofing, but I'd like to take just a couple minutes to talk about it briefly in order to motivate the work that we're doing here. So obviously spoofing is the process of a host that forges parts of the headers of IP packets in order to do something usually for a malicious purpose. So why do attackers or compromised hosts or people like that do this? So the first reason, of course, is anonymity, in order for the host to hide behind a spoof source address. There's also more sophisticated attacks that people can employ, for instance, the reflector attacks that Paxton has detailed, and of course some of the BGP TCP resets that we've heard about in the past. So there have been a string of high-profile spoofing-based DOS attacks, particularly like in 2000, 2001. We had attacks against Yahoo, eBay, E-Trade. There's worms that have been floating around, for instance, the Shaft, Trino, etc. And I tried to get some more recent data. I just did a quick scan of a DDoS website and noticed that this stuff still goes on even in 2004. So a bunch of us that were back essentially at school thinking about architectural level issues came up with this question of like, well, in essence, does spoofing even matter in 2005, right? Is this still a relevant, interesting problem? Should we even consider whether this is a problem in the architecture or not? So the sort of high level, devil's advocate is all ISPs do filtering, right? So they do RFC 2827 or unicast RPF. The second reason it may not matter is because a lot of these attackers these days are relying on huge zombie farms that provide little additional anonymity when you actually do spoofing. And then the third reason, of course, is the prevalence of NATs. As we've heard other people talk about, the headers are rewritten, and so it essentially makes spoofing useless. However, when we look at these network telescopes that people have installed around parts of the internet, we see continued strong spoofing activity. As recently as 2004, and I know people at CADA have even more recent data. So as we know from operational people obviously know, tracking spoofs is an operationally difficult problem. There was a talk at NANOG a few years back from some of the folks at UUNet. Steve Bellevin has come up with proposals for ICMP tracebacks. Other researchers have looked at things like hash-based IP traceback. All of these are designed in essence in order to track where the source of these spoofed packets are. So in order to sort of answer the question of, well, how prevalent is spoofing, or how well am I able to do spoofing, we started the Spoofer Project. And the idea here is this is quite simply just an internet-wide active measurement project where we'd like to quantify the extent and nature of source address filtering on the internet. Here's the URL for the project website. Again, the idea is quite simple. Clients simply run a spoofer binary. We also have source available, and many of you may have seen my advertisement to various mailing lists such as NANOG, CADA, some of the firewall mailing lists, etc. I'm going to get to all that in a bit. So the idea here is that the client sends a series of spoofed UDP packets, and it sends 5 of each type. The type of UDP packet we send is we specifically craft them in order to figure out and to infer specific ISP policies. I'll get into that in just a few slides. And we use a random inter-packet delay between packets in order to try to mitigate any effects that might occur from normal loss of UDP packets in the network. Each packet contains a 14-byte identifier which uniquely identifies it, and all of these packets go to a server that sits on our campus. As they're received, the packets are thrown into a database. After the client finishes sourcing all of these spoofed packets, it runs a traceroute to our server. This lets us know actually the forward path that the spoofed packets traverse in order to get to our server, and then it establishes a TCP connection that reports this traceroute, and it sends essentially a summary of all the different packets that it attempted to send in the course of doing spoofing. Two things that we do, we use UDP port 53, which is obviously DNS. This lets us hopefully get around any secondary filtering effects that people might have in place. Usually DNS can get through. We use port 80 for the TCP connection, and again, this is to get as most accurate view as possible. So the identifiers that are in each of these packets allow us to disambiguate which ones made it through. All the analysis and the web pages are driven off of this database. So I alluded to the fact that we send a series of different spoofed packets, and we try to do this in a somewhat intelligent fashion. So the first three that you see here, the first one is actually a bogon address, which means that it's a legitimate address, but it's not actually existing in the global BGP tables. The second address is a valid address in the BGP tables, except it exists, it belongs to another organization. The third one is an RFC 1918 private address, which of course is not supposed to be routable or to traverse organizational boundaries. The last one here is the neighbor spoofing, which I'll go into in more detail in a few slides as well. So here's an example of a client run. And I'll go on to some results because this is perhaps the most interesting part of my whole talk. So from March 2005, which is approximately when we announced this thing, we got about 570 client reports. Of those, about 440 were unique. And when I talk about the believed unspoofable netblocks or believed unspoofable portions of the network, I'm actually talking about portions of the network from which we did receive reports, but we see no corroborating evidence that spoofing exists. We use the University of Oregon route views table to determine things like prefix size and ASs to do all the mapping. And I should note that we do exclude a number of different classes of reports from our results. One of the things that we find is that although we have Windows clients, Windows XP Service Pack 2 specifically actually explicitly forbids creating raw sockets with spoofed IP headers. We saw about 118 of 209 reports where they were blocked. This way, other operating systems can also block creation of the raw socket. For instance, if you're running IP FW or something like that, we saw 19 of those. And of course, there's going to be hosts behind NATs where the packets make it through, but obviously the spoofing had no effect. So in sum total, approximately 2/3 of the client reports we got failed to spoof any packets whatsoever. So this is some pretty pie charts, which may or may not be misleading depending on how you interpret them. This is on our website as well. There's a continuously, actually hourly updated web page that tries to provide a view of the entire, view of the world as we've seen it in terms of spoofing. The major thing, I guess, to take away here is that no matter what metric you sort of slice the problem on today, whether it be netblocks, IP addresses, or autonomous systems, we see anywhere from 23 to 24, about a quarter of each of these, where we actually see that one of these packets that we tried to spoof actually made it through. So this corresponds to approximately 65 netblocks, corresponding to about 208 million IP addresses and 45 autonomous systems. The numbers at the bottom here are actually, if we try to extrapolate that out to the entire internet space, and I can talk about later offline if you'd like some work we did to try to say whether or not that's a reasonable assumption or not. I probably won't have time to talk about it in this talk though. So as I said, we send a number of different packets to try to infer the policies that are in place. So it's very easy for an ISP to, for instance, simply block all the RFC 1918. This is a static policy. It's never going to change, and it's fairly easy to administer. There's also, as I'm sure many of you are aware, other automated methods for doing various filtering. For instance, some providers may only allow packets to be sent or routed if there is a corresponding valid BGP route for that source. Or, for instance, the Bogon Route Server project from Rob Thomas and his crew. So here's a table that tries to capture this notion of the frequency of inconsistent filtering. So we see that, for instance, there's 17 of the sessions where the valid address was not filtered, but the bogons and the RFC 1918 were, and we see an even larger number where bogons and valids made it through, but RFC 1918 did not. And so again, this is an instance of a very specific policy. So again, I alluded to this web page. This is, I hope you'll take at least a quick look at it. This tries to summarize the current state of IP spoofing as we've seen it. So of course, our goal is to continue collecting reports in order to improve our accuracy, to get a wider view of the network, and also to detect trends. So of course, we need operator help to expand coverage and gain more data. Here's a quick view of what that page looks like. You can go to it on your own. So I also talked about this notion of the neighbor spoof that our test does. So in general, as you might expect, you're probably always going to be able to spoof your immediate neighbor IP address. So this would be your address plus or minus 1. It's usually not a problem, the exception, of course, being on some cable modem head ends and things like this. So the idea here was to actually figure out what granularity policy is applied by ISPs. So what we do is we try successively larger boundaries. We start with the /31, which is going to correspond to your immediate neighbor, go to /30, and go all the way up to the /8 to see at what granularity policy is applied. And this summarizes this. This is a probability distribution of the filtering granularity. We see spikes, as we might expect, at some of the classful boundaries. So, for instance, we see a lot of people are applying their filters on /24s and /8s. A full 40% are on the /8, which is indicative of the fact that if you're intelligent about your spoofing, you can probably do a fair amount of damage. So, the last thing I wanted to show was a visualization, actually, of looking at the spoofing, what I'm going to call the spoofing perimeter. So the idea here is that all this data in tables is nice and all, but it would be even better if we could get some reasonable idea of what the geographic spread or what the sort of extent of the spoofable portion of the network was. So what we wanted to do was to overlay the spoofable portion of the network on top of the amount of the network that we observed from all of our different clients. So we used one of Kata's tools. It's called Otter from Bradley Huffaker to build the AS graph. And each node actually on the graph corresponds to the AS for which the client belongs to. And then we also have nodes for all of the ASs along the path from that client to our server. Each edge, of course, is defined by the AS path. And we use a semi-geographic coordinate system. Again, this is similar to the Skitter AS topology graphs you may have seen from Kata. Our server is actually at the center of this graph. It's the root. And the AS hop distance is represented by the radius of each node. Finally, the node degree represents the longitude of the AS of the organization of the AS for which the client belonged to. So here's a picture. This sort of looks like soup here, but again at the center is our server. The one portion up to the right, I believe, is the US. The other is Europe, and we have Asia sitting over here. And if we overlay that with the portion of the network that's spoofable, we can get some sort of cool visualizations. And so I think I'm out of time, so I'll wrap up with that and take any questions you might have.
Nope. Okay, thanks.